Hello and welcome everyone to a Therium webinar. We're recording here in our offices at Wexford Science and Innovation. Today is Monday, November 11th. And today we're going to be talking about going beyond the numbers and really uncovering really the complex interplay of metabolites and pathways and how we use AI to really drive our insights in our reports. So I get a lot of questions asking me pretty regularly. Dr. Jasbi, I see that I'm low in my GABA levels, and should I start supplementing with GABA? Well, let's see the results of your digital twinning experiments. We run 1.3 million simulations on every metabolomic profile we generate to then produce a bespoke, personalized protocol for all of our clients. And so we have already ascertained whether or not you have low GABA levels and what impact that's having in its own metabolic pathways that it's implicated in. And our interventions are designed to bring you into homeostasis, into improved metabolic flux at retest. And so sometimes that might be GABA supplementation. Sometimes that might be theanine supplementation. Sometimes it might be improving your antioxidative capacity, reducing oxidative stress and enabling greater regeneration or enhanced preservance of GABA. So the answer isn't univariate, meaning that our interpretations go far beyond you have low GABA levels. Let's give you some GABA supplements. That is not really the ethos of multivariate and AI-driven statistics. So today we're going to go over some of these issues and what we're seeing. We'll go over metabolomics and diagnostics. We'll go over some case studies. We'll go over how this integrates into practice. And then we'll go over some digital twinning and personalized protocols and how those are generated from the metabolite data. We won't have a Q&A session. The Q&A session will be in the comments of this video. So if there is something that you'd like answers to or something maybe I forgot to cover, please, by all means, make sure you comment. Also, make sure you like and subscribe and join our channel as we will be updating our YouTube with regular videos on content that we see that our customers have ambiguities or questions about, and trying to elucidate that with some of our statistics, our own research, and as well as some findings from the field. So without further ado, let's just get into it. Really, this is the old mode of medicine, what we see depicted on the left. Basically, that you have a healthcare professional that has an issue with their client, their patient, and they're giving a therapy. Now, there's three outcomes for this therapy. This is really standard of care. What they've seen work in aggregate studies, what they've seen work in their own clinical experience, what they've been trained to provide, what pharmaceutical companies may have influenced their decision based on their sales representatives that visit their offices and their hospital systems and clinics. So they have a treatment in mind for a particular cluster of symptoms. Now, you may have three different outcomes, right? You can have an expected effect, which is what we want to see. Patient improves their condition, lab values become normalized, the patient reports a increased sense of well-being. You have no effect. And then, unfortunately, you also have adverse effects. So the goal really of our AI algorithms is to be able to complete more advanced pattern recognition, use everything from genetic information that we're provided, unique biomarkers that we elucidate, patient history, even some imaging data. And the goal is to not just identify these underlying pathologies, but also to predict these future disease risks and then develop these personalized therapies where the goal is to increase the proportion of those expected effects. So it could be that we're no longer giving the same therapy to all people, but on the figure to the right, we see that these AI-assisted personalized treatments, everyone's getting a slightly different therapy, and it is leading to a greater proportion of expected effects with reductions in no effects or those who are experiencing adverse effects. So this is, for instance, using the Rothman index, which is a simple index that can be calculated from patient metadata. It's not even from biological data, but from metadata. Yale New Haven Health Hospital System cut their mortality rate by 29%. And this is something that was, again, calculated from patient self-report and metadata, and it's included in the Epic software systems. So individuals who are practicing in those hospitals and clinics and other care facilities where they are using an Epic system, they can include the Rothman index to be calculated. And that gives usually ER nurses a better finger on the pulse as to where this patient is in their health trajectory, and ultimately helps them to have improved patient outcomes. So this is really what we are doing in our day-to-day procedures at Therium. We have metabolomics data that we collect, right? And these metabolomics data are coming from the patient, but it's also corroborated against the greater literature and what we are seeing from previous studies. That data is then undergoes significant analysis. We generate various hypotheses on this individual that are then tested using our digital twinning interventions. And that lets us see, of course, a window into diagnostics, therapeutics, and then ultimately tailoring it for personalized medicine. So this is something where you have, basic sciences meeting engineering at the intersection of statistics and bioinformatics and even molecular epidemiology. This is the life cycle, and this is a article we published earlier this year in Biomedicines, where we show how we go from analytics, which are really just statistics that are reported in various studies, to generate the data from patient samples, as well as some self-report data that we get from our customers using our Omni survey, and how these are merged together to form actionable next steps via interventions that we may recommend to improve the metabolite levels and ultimately improve the health domain scores that we test here at Therium. So just a quick review of what metabolomics is. It's a comparative science, meaning that we're usually comparing treatment to control. We're comparing disease to no evidence of disease. We're comparing surgical intervention to sham surgery, whatever the case may be. We may do this in various model organisms, whether it's cells, whether it's mice, whether it's humans. We can do this in various biospecimens, whether it's feces or urine or cerebral spinal fluid or blood spots, as we do at Therium with our Aristotle test. As a whole, the science uses primarily two main platforms, mass spec and NMR. Mass spec is generally favored due to its increased sensitivity, though NMR does have quantitative capacity and is also non-destructive. So there are pros and cons, but for our purposes, mass spec is preferred given its increased sensitivity. In fact, it's 10 to the 6 times more sensitive. So what we do is we identify and quantify those metabolites. We then generate biomarkers for various things. Those can be everything from compliance of diet diversity, looking at screen time, looking at sarcopenia. We have biomarkers for non-traffic related air pollution. We have biomarkers for aquatoxins. We have biomarkers for cancers. We have biomarkers. We have over 15,800 different models for which we have biomarkers from, and those are mined mostly from scientific literature, either published works or raw data that we mine from depositories. That modeling lets us to identify drug targets. It serves as a bridge for medical translation between previous studies that have validated their models either through internal or external validation methods. It allows us to look at an objective marker of diet. It lets us look at various processes and pathways that may be perturbed in early disease progression. And so this is where metabolomics, of course, comes in handy, right? Metabolomics, as you can see here in this figure, is downstream of all the other systems biology levels. So nuclear DNA has to be expressed, transcribed to RNA, which then has to be translated to proteins. And these are all very important layers of systems biology, but metabolomics actually lies at this intersection between the genome and the environment. And I've said this multiple times, many times before in other videos, but I'll say it again. Most diseases, the ones that are the greatest contributors to human morbidity and mortality, they are not due to genes. They're not genetic diseases, I should say. They're more genomic diseases, meaning that there's no handful or half dozen genes that can, with high accuracy, predict cardiovascular disease, cancers, neurodegenerative disorders, even metabolic disorders in most individuals. And with high accuracy, I mean usually 90% accuracy or greater. More likely, and what the data have shown, are that these diseases, heart disease, cancers, neurodegenerative disorders, and the like, the usual suspects and the greatest contributors to human morbidity and mortality, these are genomic disorders, meaning that there's usually a dozen to a few dozen genes that explain some variance in that patient's outcome. And they cannot be used by themselves to then predict with 90% accuracy whether an individual will develop heart disease or schizophrenia or pancreatic cancer. In fact, there are some genes, like the gene for Huntington's, that has great, very high penetrance, meaning that if a person has this variant, they will inevitably develop Huntington's, right? And there are ways to stave off or treat symptoms, but the Huntington's pathogenesis is an inevitability, essentially. But again, for most of those conditions, that's not the case. So most of these conditions are the result of gene environment interactions. So we see in the figure to the right, we see that the genome is at the highest level, and then we see metabolomics there at the bottom of the hierarchy, and then we see phenotypic change, and that phenotypic change is really the environment as well. So the environment is impacting the phenotype, right? And you have the genome that is essentially shifting probabilities on a large scale towards favorable health outcomes or detrimental health outcomes like disease. So, for instance, if you have the genes for schizophrenia, of which there's about half a dozen that have strong implications in the onset of schizoid and schizoaffective disorders, you have a very broad probability of developing schizophrenia, but it doesn't mean that you will, in fact. And so what do you need to develop schizophrenia is maybe some genes, but also correct transcription and translation of those RNA and proteins, respectively, correct protein folding, protein-protein interactions, microbiome interactions, but also psychological events in the environment that may trigger the onset of schizophrenia. For instance, you may have certain stressors, you may have traumatic stress, you may have abuse, you may have neglect, and a lot of these environmental factors can lead to schizophrenia if the genes are present. And so when you want to look at the onset of schizophrenia, what should you look at? You should look at the intersection between the genes and the environment. Now, that intersection is necessarily metabolomics. And the research has shown that metabolomics is a more sensitive and specific indicator of current health states, whereas the genome tends to assert very broad probabilities. For instance, you may have a 20 to 80% chance of developing breast cancer, depending on your BRCA1/2 mutations. Metabolomics allows us to query the metabolism using these very sensitive biomarkers and roughly gauge, let's say, a metabolic overlap between your profile and the known profile of breast cancer at various stages, given a certain subset of metabolic biomarkers. So again, metabolomics sits at that intersection point between the genes and the environment, and is a very attractive layer to probe when we want to ascertain the current state of dynamic health modules like metabolic pathways. So moving on, let's take a look at what metabolism is. Here, we see 80 canonical pathways for Homo sapiens that are indexed in the KEGG database, the Kyoto Encyclopedia of Genes and Genomes. And this is kind of like a Rosetta Stone for scientists. This allows us to say TCA cycle, and we now have standardized what we mean by that. What are the genes and proteins and metabolites and functional nodes of that discrete pathway, the TCA cycle. So here we see all of them mapped from the KEGG database. In this next slide, we're going to see what we can monitor with our Aristotle test. And as you can see, about 68% of all metabolic pathways reliably being monitored with 2 metabolites or more using the Aristotle test. And this is because we leverage the redundancy that's inherent in biology by monitoring sentinel metabolites, such that by monitoring 1 metabolite, we gain access to 3, 4, 5 different pathways at once. And when we monitor 126 of them, we increase our coverage of the metabolome to 68%. Now, we can also compare this to metabolite coverage using a complete blood count, basic metabolic panel, lipids test, liver function tests, thyroid function tests, and the organic amino acids tests, the OAT test. So we see here in red, this is the combined coverage of those 6 tests. There's a lot of overlap with our Aristotle assay, but as you can see with our metabolomics panel, we are still capturing far more metabolic pathways, and we have a far greater, significantly greater coverage of the metabolome as compared to these 6 tests combined. So that's all to say that we are collecting a lot of data. And the data is not just univariate single point interpretations. As I mentioned, 1 metabolite may be involved in different pathways. So affecting the levels of 1 metabolite doesn't just affect one thing. It in fact moves certain pathways. It shifts certain pathways, sort of left or right of center. And one intervention generally has a cascade of effects. That's what this means to show, is that we're collecting a lot of data, and it's very difficult to interpret that data based on low or high levels of just 1 or even a handful of metabolites. But it's really the complete picture that has to be analyzed, and that's where we get the greatest impact and vertical advancements in customer health, is by analyzing the totality of the data we collect as one whole, as a synergistic endeavor, rather than univariate interpretations that are often misleading or even false. So real quick, what is our test? The Aristotle test, if you're not already familiar with it, is a dry blood spot. So you get a kit at home. That kit is then sampled with a finger prick. It's put on a dry blood spot card. It then comes back to our lab here in downtown Phoenix for processing with gas chromatography, mass spectrometry. And that lets us look into 126 metabolites that are sentinel metabolites again, and give us coverage of that 68% of all known human metabolism we saw earlier. On the right, you see the concept of digital twinning. What we are doing then is creating a mathematical abstraction of that individual. That abstraction is designed to serve as a guinea pig, essentially, a digital guinea pig. What we do to that metabolomic profile is then simulate the effects of 1,300 interventions that we have mined from scientific literature. These can be everything from supplementation, over-the-counter supplementation, certain prescription medications, dietary changes, lifestyle changes, like exercise changes, or even changes to the built environment, like water filtration system or air purifiers. It may even be certain behavioral sessions, like mindfulness training or cognitive behavioral therapy. These are all indexed from the literature, meaning we have looked at studies that have performed some intervention like this on their human subjects, and they have seen certain effect sizes, variations, effect heterogeneity, improvements or declines in these metabolite levels specifically. What we're doing is we're simulating the effects of those on your digital twin so that we can sift through these 1,300 interventions and figure out what is best for your metabolic profile, given the response of your digital twin. If we give your digital twin 400 milligrams of magnesium, What does that do? What if we give it 200 milligrams of magnesium glycinate? What does that do? What if we gave it 200 milligrams in the morning and 200 milligrams at night? What if we gave you the supplementation on an empty stomach or with a meal? All of these can be more or less modeled, given the data that we have to support it from the scientific literature, can be more or less modeled. And then the response from your digital twin is indexed using various statistical outcomes like mean decrease in accuracy or variable importance and projection. And those statistics allow us to then take those 1,300 interventions and sort them from most effective to least effective to those that are maybe even predicted to be detrimental to your metabolic profile. And we're able to create a very bespoke protocol for all the 12 health domains that we monitor, like aging, like mitochondrial health, like liver health, like environmental toxin score, right? Um, so what does that really look like? Here we have this visual, and this visual is going to show the positive and negative correlations across these 126 metabolites. As you can see, the correlations are immense. It is not just about a single metabolite. It is about one metabolite that's correlated with 126 metabolites, the second metabolite that's correlated with another 126 metabolites. And these are interconnected, and they show the interconnectedness of the pathways and how they impact the health outcomes. And so we leverage these correlations really for holistic insights. This is, again, showing that the human brain might be able to handle one metabolite, two metabolites, maybe a couple dozen metabolites and their levels individually. But the human brain will struggle to identify the patterns of these metabolites across pathways. The human brain will also struggle to make meaning of these correlations. And one metabolite might be high, but if its correlation with another metabolite shows that this is, in fact, a healthful increase, and that it's okay in this instance for this metabolite to be above the reference average set for it, the interpretation and then subsequently the intervention that follows will be completely different. So once we start to get to 126 metabolites, many of which are represented across multiple pathways, it becomes impossible for the human brain to calculate the health state of an individual. It also becomes impossible for the human brain to then map that to the metabolism and then suggest cogent therapies to improve that patient's health. So we know now that these, as you've seen, it's not just about a single metabolite. It is about that metabolite's correlations across 125 other metabolites. And of course, this becomes impossible for the human brain to keep track of, to reliably assess the health of a domain like liver or the cardiovascular system, which uses dozens of these metabolites and their correlations to score. And so we need multivariate statistics and AI-driven algorithms to then go through this data, recognize certain patterns, and return results. And this next slide here, what you're seeing is, here we go, and I can share it. If I shared it, that would be helpful. What you're seeing in this slide is TCA cycle metabolites over time. And what you're seeing is across months of this individual, we are seeing this interconnected flux. And our AI models can actually model these dynamic shifts across time. And this is really, again, speaking to the complexity of systemic metabolic regulation. It's that it's very difficult to look at glucose or pyruvate or lactate or alanine or citrate individually, and really be able to track its progress through time and be able to make discrete interpretations of what that means for a customer. It might be possible with a few metabolites, but when we have all these metabolites of the TCA cycle and some of the metabolites preceding it from glycolysis, it is impossible then for the human brain to map all of these reliably in their brain to those pathways from glycolysis down through the oxidative phosphorylation cycle of the TCA cycle and be able to present a cogent interpretation, it then becomes really an extraordinary feat to be able to monitor these dozen or so metabolites through time, so that when a physician retests an individual between these months, they have to then go back and analyze what that previous month's results were. Are they going up? Is the flux going down? Are they going back up again? With our systems, we are able to automatically keep track of a patient's metabolite levels through time and decipher these longitudinal trends that are not readily attainable by the human mind, by any physician interpretation, store that data for that individual through time, and then again, with our modeling methods, be able to discern very minute idiosyncrasies that the human brain would not capture, but to the artificial intelligence signals some metabolic aberration that can then be directly targeted with interventions mined from the literature. So this slide shows a machine learning driven decision tree. It's essentially the process for metabolite restoration. So it really shows how our AI tends to process these complex patterns across multiple metabolites to make these recommendations. So let's walk through it and see some key points here. What you'll see are these decision nodes, and each node really represents a point where the AI splits the data, and it's based on a metabolite threshold, such as M2 or M3 or M7. These thresholds aren't arbitrary, okay? They reflect the levels at which changes in these metabolites balance really significantly impact these overall health outcomes. For instance, if we see that the AI here is evaluating whether the level of M2 is above or below 0.02 to make the first split. So that determines the likelihood of recommending that intervention. Then we see the Gini index. Now, it's shown in each node, but it measures essentially how pure each split is. So a lower Gini value indicates really a clearer, more decisive separation between classes, is either going to recommend an intervention or not. For example, we see nodes with a Gini of 0, such as the orange boxes. These are entirely pure, meaning that all samples in those nodes belong to a single class, or all metabolites in those nodes, I should say, belong to a single class. So the clarity reinforces the confidence of the AI's decision at these points. So we also see sample distribution in the bracketed values, such as 43, 57. Okay, so that shows how samples are distributed between the two classes within each node. So those numbers really help us to understand the balance of the intervention versus no intervention. And that really informs recommendations of each step. For instance, at the root node, we see a split of 43 to 57, showing a fairly balanced data set, while the later nodes reflect pure divisions. Now, we also want to know, what is the purpose of this? Why am I showing this? This is really the process that our AI uses to account for the complex multivariate relationships that are not obvious through traditional analysis. And by systemically evaluating these patterns across multiple metabolites, the AI can recommend very precise, individualized recommendations, considering, of course, how metabolites interact with one another in those metabolic pathways we showed earlier. So again, this decision tree that I'm showing here that I've queried from our AI, this is on real data, it really showcases the advanced bioinformatics and the AI capabilities that we have here at Therium. It emphasizes how our recommendations are really rooted in these deep data-driven approaches, and they go far beyond the traditional approaches that physicians have to rely on, that are really more simplistic and single metabolite based interpretation. So it allows us essentially to deliver much more effective and targeted treatments for our clients. Now, here we're seeing the overall workflow for patient integration and management at Therium. So a patient approaches one of our Therium physicians, and they have a cluster of symptoms. That physician will then order a Aristotle test for them. That comes back, is analyzed with our mass spec, and then that undergoes certain analyses and data acquisition, of course. So we have algorithms that will then go through the collected mass spec data to pick peaks and generate the data that we use for scoring individuals across health domains, as well as the digital twinning that we may, of course, use to provide personalized protocols. And this is going through two means. So obviously, the data goes through our predictive AI for assisted modeling and processing, but it also goes through a human scientist that then reviews this data. And so we have sort of unsupervised methods like AI, as well as supervised methods, which is the lab scientist, right? And so that really ensures that there is a very accurate domain analysis with a robust set of precise protocols to affect, or I should say, ameliorate the detected metabolic aberrations, and then a clear trajectory for improving these patients' health scores through time. So this is really the workflow, and although we use AI, of course, in analyzing a patient's health state and then recommending protocols to improve that health state, all of these protocols are checked by a lab scientist to ensure that there's no discrepancies in dosage, contraindications between supplements and medications, that although the AI is trained to detect, AIs do still from time to time hallucinate and make mistakes. So it is always important to have human analysis that then feeds back to the patient and the physician. And so this is to say that not only are we more accurate, which we'll show in the upcoming slide, but it is vastly quicker. It is 120 to 240 times faster than traditional computing methods. So if a physician were to even set up, automated computation sheets whereby they dropped in the metabolite values and were able to score and analyze the flux and throughput of certain pathways, that is still going to take roughly 240 times slower than if we were to run it through our AI and collect that data and those insights. Now, what about predictive accuracy? So this slide is going to compare the predictive accuracy of our AI versus traditional interpretation methods. So what we see here is that our AI model achieves an accuracy of 92%, which is significantly higher than traditional methods, which are about 65% accurate. So this means that the AI's predictions and health recommendations are more likely to be correct, and therefore more likely to improve outcomes for users. Now, in contrast, the traditional methods, which are, of course, physician review, they reach only about 65% accuracy. And that's not the physician's fault. Keep in mind, this is a lot of data to go through. These are not simple blood work panels. These are highly orchestrated and detailed metabolic profiles that, again, have been curated with an eye toward increasing metabolome coverage. Now, this lower accuracy often results from relying on single biomarkers, like someone's GABA is low, so let's give them GABA, or simple thresholds. And these don't really capture the complexity of the interdependent metabolic pathways. Now, the AI's model accuracy, again, it's significantly higher, and it really highlights its ability to analyze these complex multivariate data, and it's synthesizing insights from various metabolite levels, not just one. More importantly, it's using correlational patterns to also bring new insights that are not, again, readily attainable by the human practitioner. Now, this multivariate approach is really essential for accurately predicting these health states and then recommending effective interventions. So with the AI model, we're able to provide reliable and precise health recommendations. And this is a really crucial advantage for Therium because it allows us to support users with insights that are really account for the interconnected nature of the body processes. The metabolism is not just one or two pathways, and it's not one or two metabolites or one or two genes. It is a orchestrated, complex interplay of these dynamic factors that appear in more than one area. And so again, one intervention will have necessarily cascading effects that need to be accounted for. So again, this slide is really designed to just underscore the power of AI and move beyond traditional simplistic interpretations. So this slide again shows metabolite interaction heat map with a focus on pre and post pathways, post intervention. So here we see the pre and post intervention comparison, and the heat map visually contrasts the metabolite interactions before and after an intervention. So the comparison, see here, shows us basically how intervention shifts relationships between various metabolites. It's showing the direct and indirect effects it has on the metabolic network. We can see that the red cells represent positive correlations where metabolites tend to increase or decrease together. And the blue cells show negative correlations, or where the increase of one metabolite really correlates with the decrease of another. And so this is really just a quick color coding that helps us identify these clusters of metabolites that are tightly linked. And the heat map illustrates that an intervention doesn't just impact a single metabolite, but cascades across multiple pathways. The visual pattern changes after the intervention, and that really highlights the complexity of the body's response. And again, underscores why these simplistic single metabolite approaches tend to miss these broader effects. And there are key insights, right? So, what we can really tell from this is that the complexity of metabolic adjustment in response to interventions is vast. And that you need to use a AI that can leverage these insights to recommend interventions that are going to consider both the impacts and systemic shifts across the entire metabolome that is being monitored, which again, traditional approaches do overlook. So again, our approach to health is not just about addressing individual deficiencies, but understanding and optimizing the broader network of metabolic interactions. And so, again, AI-driven recommendations, like the interventions that are populated with our digital twinning process, these are more comprehensive and impactful. Now, here we have um, really a digital twinning technology where we show with the baseline is in yellow, an individual who was low on GABA, three individuals, I should say, who were low on GABA. The first individual, this is baseline. This is an individual, as you can see, that all three individuals here, those who were baseline, meaning that they did not receive any interventions and they did not implement any pharmacological changes, that is shown in the yellow line. An individual who was not given a GABA supplementation as part of their recommendation, but started consuming GABA themselves is shown in the orange line. And then we have in the red line an individual who, again, at their initial testing period, was low on GABA and was given different recommendations, but none of them were directly related to GABA supplementation. Now we can see that at baseline here, all of these individuals are roughly at the same level. You can see that the person who then took the GABA supplement and the person who did not take any interventions or GABA supplementation whatsoever, they are roughly in the same, GABA concentrations right here at month 0. Right. But albeit the AI recommended individual who was taking the interventions from our digital twinning platform that did not include GABA supplementation directly, he's a little bit higher, but not by much. All three individuals are clinically depleted of GABA. Now, what we have again is testing through time. This is at months 2, 4, 6, 8, and 10 for all three individuals. And what we are seeing is that, again, the yellow line took no supplementation for GABA. So this is really the line represents the natural progression of metabolite levels over time without any intervention. In the case of this discussion, this can serve as our control. So it shows how levels would change in the absence of any intervention. That's the yellow line. Now, in the orange line, we see the GABA levels for an individual who was supplementing with GABA directly. Now, while there is an increase, it's relatively moderate and slower over time. Now, this line demonstrates a more linear but less optimized approach. It raises the metabolite levels, but it doesn't account for other metabolic interactions or the body's underlying dynamics. Now, in the red line, we see an individual who, again, at baseline was clinically depleted in GABA, however, was not given, sort of counterintuitively by their physician, reading the report, this physician asked, well, their GABA levels are low. Why are they not being given GABA supplementation? Well, this individual was being given theanine. This individual was also being given a very a diet that is going to generate GABA from interactions with the gut microbiome. This person was also being put on a anti-inflammatory supplement stack, and also being given mindfulness sessions. I believe it was 20 minutes a week of mindfulness. And so there was no direct GABA supplementation in that red line that we see. But because of the interconnectedness of the metabolic pathways, as we've discussed, this individual actually significantly increased their GABA levels at 10 months compared to the person who ignored the protocol and decided that they should start supplementing with GABA. And these are three real people from our databases that are demographically matched, although they tested in different times of the year. So there may be some seasonal fluctuation. But overall, we do see again that with no change, you might still get an increase in underlying metabolite levels. If you sort of go off script and ignore the protocol that we generate via our digital twinning protocol, you may and then supplement with those metabolites that you're low in. You may experience an increase. In fact, you probably will, although you're risking detriment in other health domains. And this individual in the red line who did not receive direct GABA supplementation, but instead through behavioral changes like mindfulness practices and meditation, changes in the diet, as well as supplementation with a precursor, actually had far greater increases in GABA levels starting at 4 months and continuing up to 10 months. So this is an individual who tested with us as well. This is a 62-year-old Hispanic female. She's a retired OBGYN here in Scottsdale. She is reporting numerous known diseases as well as a litany of medications and supplements that she's taking. This was her score that we tested at baseline. And then at follow-up, so at baseline, we tested her, we gave her certain recommendations, and some of these recommendations are actually in the supplements that she's reporting. For instance, spermidine or collagen, protein, liposomal glycine, resveratrol, carnitine, CoQ10, magnesium, threonate, glutathione. And these are from her survey responses. So we can see that in this individual, we had significant improvements at retest. At baseline, all of her scores, with the exception of 3 of them, were all poor. Very low nutrition score, very low inflammatory score, very low cardiovascular, reproductive liver scores, terrible. Neurocognitive scores down through mutational load, all very poor scores. She had 3 scores that were okay. 2 of them were normative, meaning that they're consistent with her age and sex. So her aging and her gut profiles were normative. And her mitochondria were actually doing really well. So even at baseline, her mitochondrial score is a 9. Now, again, this is the interconnectedness of pathways, and sometimes improving or engineering a health trajectory can be a zero-sum game, meaning that you're going to make certain concessions to then gain improvements in other areas. So at retest, we improved all of her scores with as little as an improvement of 2 scores. 2 points, with her aging index going from a 4 to a 6. Her gut profile stayed the same, 7, and her mitochondrial score went down by 1 point. However, as we can see in those domains that were significantly lower, like nutrition or inflammation, but particularly reproductive, liver, neurocognitive, integumentary, environmental toxicity, and mutational load, she gained anywhere from 4 to 7 points at retest. Okay, so what is the cause of this? How did we go from really a depleted profile to an individual that is then bordering on optimization, on real health optimization? So we see here in her profile that we have certain issues that were detected at her baseline test. So her baseline test was February 4th. Her recommended retest was May 4th. She did not retest with us until June 6th. She will retest with us upcoming here and on December 6th. It's today is November 11th. So her next retest period is December 6th. So she went from having elevated oxidative and DNA damage markers, dysregulation in DNA repair pathways, increases in 8-OHDG levels. These are the aberrations that the AI is detecting, and we can ask the AI to create these sort of Gantt-like charts for us so we can track patient progress through time. This individual also had elevated levels of heavy metals, lead, mercury, aberrations in detoxification pathways, elevated oxidative stress markers. You'll see that very rarely do you see a single metabolite be a cause of concern. We do see that here with the mutational load, the increase 8-OHDG levels. That's a single metabolite interpretation, but every other metabolic aberration that is being detected in this individual is a large scale aberration that is really contingent on pathway flux rather than a single metabolite level being high or low. We're seeing dysbiosis in gut microbiota composition, elevated levels of zonulin, decreased short chain fatty acid metabolism. In some cases, like reproductive health, we're not actually seeing any direct metabolic aberrations being identified. We're seeing dysregulation in the electron transport chain, decreased CoQ10 levels. For mitochondrial health and the inflammatory index, we're seeing aberrations in NF-kappa beta signaling. We're seeing TNF alpha and IL-6 most likely being elevated given our levels. Here we do see decreased glutathione levels as a significant contributor to that low inflammatory index. So we can map our interventions onto the detected metabolic aberration. So what we see here is that we have, for instance, we had elevated oxidative DNA damage markers, dysregulation DNA repair pathways, and increased 8-OHDG levels. How are we addressing that? Antioxidants and polyphenol-rich foods, sleep quality and stress management, and regular health checkups to monitor levels of that metabolite. We're seeing elevated levels of heavy metals, aberrations in detoxification pathways, and elevated oxidative stress markers for her environmental toxicity domain. How are we addressing that? Air purifiers and detoxifying foods, reduce plastic use, safe household cleaners, regular exercise. Let's go down to liver health. We're seeing aberrations in phase 1 and phase 2 liver detoxification pathways. We're seeing elevated, most likely ALT and AST levels. We're also seeing decreased glutathione levels. How are we addressing that? We're giving her cruciferous vegetables, which have a lot of the precursors for cofactors in phase 1 and phase 2 metabolism. We're also giving her a relatively moderate dose of milk thistle, 150 milligrams twice a day. That is going to, of course, impact the ALT and AST levels by increasing hepatogenesis and the hepatic repair rate. We're, for instance, in cardiovascular health, seeing aberrations in lipid metabolism. This is not just one metabolite, but a string of fatty acids that we're seeing. Elevated LDL and triglycerides are being inferred, as well as decreased HDL. How are we addressing that? Reduce saturated fat intake, obviously. So her palmitic acid levels are probably very high. Oleic acid levels are probably very low. Fiber-rich keto foods, and then red yeast rice extract at 900 milligrams a day. For her mitochondrial health, we're seeing dysregulation in the electron transport chain. We're seeing decreased CoQ10 levels and elevated activity of reactive oxygen species. For that, we're giving CoQ10 at 200 milligrams a day and alpha-lipoic acid at 600 milligrams a day. Again, these interventions are not designed to increase or decrease one metabolite, but increase or decrease entire pathways and processes. Okay. Now, we retested her June 6th. Obviously, she had a retest timeline scheduled for May 4th. We retested her on June 6th, and we still saw persistent DNA damage. The DNA repair pathway dysregulation went away, but now we're seeing aberrations in P53 signaling pathways. We also saw elevated levels of DNA adducts. For instance, in her aging index, we saw aberrations in polyamine biosynthesis pathways, which we then supplemented with spermidine supplementation, omega fatty 3 acids, and mindful movement like yoga or Tai Chi. However, at retest, we saw persistent dysregulation of polyamine metabolism, increased levels of N1-acetylspermidine, and aberrations in NAD plus metabolism. So that will then trigger a new set of recommendations designed to address what is persisting from the initial testing instance, as well as new issues that may come up given changes in her diet lifestyle, and of course, what we've recommended via digital twinning. Now, what we can actually show is that she has 12 scores that we look at, overall score, as well as domain scores for each one of these individuals. And what we're showing is that there are actually 5 factors that are underlying her improved health trajectory. So this is her February 4th testing instance. At June 6th, we saw significant improvements. And then we postulate that December 6th, where she's scheduled to retest, we will have many scores, be a perfect 10. We should see some of her scores no lower than really a 7, right? 7 will be her lowest score. But all of these scores are actually being mitigated by 5 processes, which we can model using a factor analysis approach. And those are the predicted slope equations for each of those processes. For this individual, that was lipid peroxidation, that was decreased mitochondrial oxidative phosphorylation. It was phase 2 liver metabolism, collagen synthesis of all things, as well as gut-derived inflammation. So these are the 5 factors that we are modeling for this individual. And if we address these 5 underlying factors, given the metabolites that we are detecting and the interventions that we're recommending, again, we should see significant improvements in all of these domains at retest. So again, this is not just about looking at individual metabolites and saying you are low in malic acid, have 1 medium apple a day to bring your malic acid levels up. Sometimes that may be the recommendation, but oftentimes we are trying to address pathways and processes because disease does not happen at a single metabolite level. Disease happens at a pathway level. It happens at a process level. So by analyzing the 126 metabolites, not just in a vacuum, but in the interconnected nature of their function in those metabolic pathways, we are able to decipher these bottlenecks and the ubiquitous aberrations that we detect across the 68% of metabolism that we monitor with the Aristotle test, assess the underlying factors that are impeding or, again, might be the key to improving those scores, and then use targeted interventions simulated from the scientific literature to improve those scores. So oftentimes, like we saw, an individual who is not taking directly GABA supplementation, but is taking precursors, dietary changes, and behavioral changes, will in fact experience greater levels of GABA through a 10-month time period as compared to an individual who was taking GABA supplementation or an individual who was taking no supplementation, no intervention, but still had a similar increase in GABA levels. So this talk is designed to really highlight and underscore the complex nature of metabolism and impress upon our practitioners, our direct-to-customer users, that it is not just about univariate metabolites. And if you're going through your report and you see you're low in something, please do not feel like you need to then go and supplement with that thing if it's not in your digital twinning protocol. Your digital twinning protocol has taken a systems biology network approach to this analysis, and the things that we're recommending are designed to synergize together to improve your health outcomes. So that would be it for me today. If you guys have any questions, please let us know. You can go to www.therio.me for our webpage. You can also use that booking page to book a training session with Dr. Greg Nacarelli. He's one of our physician scientists on the team, and he can go over any questions you may have of what the Aristotle test is, how to get started, what testing looks like, the process of it, cost, time to analysis, everything that's really related to our services. Dr. Nacarelli is a fantastic resource for that. This is Wexford Science and Technology, our laboratory where I'm broadcasting today. And again, if you have any questions, you can email us also at info@therio.me or call us at that 844 number. And again, wishing you the best of health. I'm Dr. Paniz Jasbi. Thank you so much for tuning in. And I hope this has been helpful in understanding the complexities of AI analysis and how we at Therium use this to go beyond the numbers and drive your health in a vertical, impactful manner.